All right, so good morning. Today we get to fire as a laser. All right. So, Austin Powers, I don't know if that's like a reference anymore. Do y'all get that? Do y'all know Austin Powers? Yeah, that's right. And that crazy lady, as a laser. Yeah. Anyway, lasers have an interesting reputation. And so we're gonna learn a little bit about them today. So we've talked about line spectra of atoms and so on, and the first lasers were made using atoms, atomic spectra. And so they have very, very narrow line widths. And this is the helium line spectrum. And you can compare that to our solar spectrum, which is a continuum. So when we talk about continuum spectrum or line spectrum, just to want to reinforce that a line spectrum is a specific spectral line. And so we're going to understand what's giving us this sharp line in helium today. And so that's, if you put that emission inside a resonant cavity, and a resonant cavity is just two mirrors facing each other, and you have the emitter inside, that light can go back and forth between those two cavities. But you don't really get amplification until you have a population inversion. So we're going to talk a little bit about that today. And then I have show and tell today. So I've got this blue laser out of a Blu-ray CD or DVD player that a student of mine took apart, and he made this little handheld laser. And you can get lasers in all these different colors, because you can imagine if you've gone to a fireworks show, every different color that you see in the fireworks, that's atomic emission. So they take salts like strontium chloride or whatever, and they mix it in with the gunpowder, and they blow this mortar up in the air, and it's burning through the paper, and then it gets to the inside, and then it blows up that little bag of gunpowder with strontium salt in it, and you see red light coming out because of those strontium atoms. And so every light that you get out of an atomic emission in a firework, you could make a laser out of that if you could figure out a way to get that atom to be in an inverted population, because that's how you get the stimulated emission. So this is this light laser. So it is really bright. I'm not going to hold it on any one spot on that screen because I don't want it to burn the screen. This laser is not eye safe, so I'm going to not ever point it at you or me. Okay. The reflection is somewhat eye safe, but if you look at it, like if you stare at it, then look somewhere else, you can kind of see a dark spot. So that's a bad thing. But you're just bleaching out the rods and cones. You're not harming yourself, but it's just like getting a flash photography, a bright flash in your face. You have that spot for a while. Or when you're driving in on Highway 30 and the sunrise hits you. Right there, we're past the day, but there's a day in the spring and the fall. It's not exactly on the equinox, but it's close, when that sun is right on the road. And I'm there at the Veterans Memorial Light, and I happen to look up and I get the sun, and then I can't even see whether it's green or red because it's right there where I'm focusing. And so, yes, there's the lady, fires the laser. I love this too. Don't chase the laser, Carl. It's what the humans want. And then me not trying to offend anyone in 2020 or 2021. Anyway, the struggle is real. So we have this Jablonski diagram where we pump these atoms up. So this absorption, if you have a strong absorption, then you can pump the molecules or atoms in that little pachinko game. Like I was saying, you keep banging that lever and you get all of these molecules up here in this level. And if you get more molecules here than down here, you have a population inversion. That's the key to lasers. You cannot have a laser without a population inversion. In general, I don't know of another way to do that. Because as soon as one of these little molecules or whatever drops down through a fluorescence, then it can stimulate the others to drop down. And that's the key. It's the stimulated emission that gives you the amplification of light. So here it is in sort of a slow animation. So as you hit this ground state atom or molecule with light, you excite it to some other state. Now this is the 4-level system for the neodymium YAG laser. It's a very common laser. Neodymium is a rare earth element, but there's plenty of it to make these garnet crystals. It's an aluminum garnet crystal. So the crystal structure of this laser rod, this lasing medium, it's a crystal. It looks like a glass rod, but it's a crystalline structure. And they take out its yttrium aluminum garnet structure. and then they take out some of the yttrium atoms and dope in neodymium. And so it's the neodymium energy levels that we have here. They want it to be in a crystal structure so that these energy levels are all in the same environment. So there's a very well-defined energy difference. If you have an amorphous crystal like a glass, then some of these energy differences will be detuned. They'll be in a different environment, and so you'll get kind of a scrambling of the energy levels, and that just widens the width of your laser. So if you want a really narrow, high-resolution laser, you want a perfect crystal, and they'll grow these crystals really slowly out of a molten aluminum garnet, thing, and they'll just pull on this crystal very slowly so that they make a perfect crystal structure at the right proportion of yttrium and neodymium and so on. So as you continue to pump this neodymium system up, some of them don't make it, some of them go around and they get stuck in that metastable state. Notice this is fast pumping, so it's a it's a large absorption peak. So you pump them up to this state, and then they relax down to this state, which is they call a metastable state. They stay there for a little while, but then you have this slow emission where some of those drop down and go back to the ground state. Think of it like a funnel. Okay, a funnel leaks, right? But if you put the water in fast enough, you can fill that funnel. And so this up here is a funnel, and we're filling that funnel. And the nice thing is the lasing lower level is not the ground state. It's pretty hard to get an inversion, a population inversion against the ground state, because that's where all of the ground state atoms are. But if you have a state that's close to the ground state, but not quite, then you can get a population inversion pretty easily. Here we've only pumped 3 neodymium atoms up here, and we have a population inversion with respect to this level. And so we could make a laser with this level right here. So thermal equilibrium is shown over here on the right, where you have essentially all of these different systems. So these are, say, individual neodymium atoms. So it's not a single atom with all those energy levels. This is atom 1, this is atom 2, this is atom 3, this is atom 4. And at thermal equilibrium, you only have one excited atom, and the rest are the ground state atoms. But if you could get a population inversion here, we have 5 atoms in the excited state and only 4 in the ground state. And that's what we're talking about in terms of a population inversion. And so if we get enough of these molecules up here in the upper state, then we can have a pretty intense laser. So we pump that up with visible light, and this is the construction of the type of lasers we used in my graduate days. Is we have this flash lamp here that puts out visible light, and it's in this pumping chamber. This is an aluminum block with a mirrored inside, and it's an ellipse. And so this is at one focal point of the ellipse, this is at the other focal point of the ellipse. And so all the photons that come out of that visible flash lamp go in and pump that laser rod. So they come off of this mirror and they all go inside that laser rod. So all that light is being pumped into the laser rod. So that's why we mean this efficient pumping. We're just driving all of those neodymium atoms to the excited state, because the more that are up there, the brighter the laser. Okay, and then when that laser rod starts to emit, some of that light bounces off these mirrors, and so this is the resonant cavity. So this right here is that resonant cavity. Have you ever been to, let's see, they had one in, this is kind of, and it was called the Exploratorium. It was a kids museum in San Francisco, where they had these parabolic reflectors, but it was for sound. It was a resonant cavity for sound. Or if you've been to the Capitol and you sit where, was it Adams's desk? And anyway, there were 2 desks in the Capitol and the dome, and you could whisper at this spot and they could hear you over that, but nobody else could hear you. So that was a resonant cavity through that dome. Or in this museum, it was like maybe like 100 feet across, and you could sit on this little chair in front of this parabolic concrete wall, and you could whisper, and a person sitting in the other chair could hear you. So all of your sound would bounce off and go straight across the room and bounce off that and go into their head, like right close to their ears. And and in between, your sound was really spread out, and so people couldn't hear you in between. Okay, and so my sister is way over there, and I'm talking to her, and she's like, "Oh, this is crazy. I can hear you." I said, "Yeah, I can hear you too." And she said, "Can they hear us in between?" I said, "I don't think so." And she said, "How do you know?" And I said, "Because that lady's hair looks ridiculous." And the lady never looked. And my sister was like, I said, "See, they can't hear you." And so between these resonant cavities, instead of sound, we're dealing with light. And so all that resonant cavity has to be is tuned to a particular wavelength of light. And so there's multiple wavelengths of light in there, and then you get a standing wave in between those two mirrors. And then you just either partially coat this front mirror with a little bit of metal so it's not 100% reflective, or you put a pinhole in it. But anyway, you let light leak out. So in these lasers, we have a resonant cavity, and that's just light that's leaking out. So inside that resonant cavity, it's incredibly bright. This is just the amount of light that's leaking out. Now, when you turn the power off, it all leaks out, but it's just letting a little bit of the light out at a time. Now, for flash lamp driven lasers like this, you need an incredibly large power supply. And I talked about that earlier. I showed some pictures when we were dealing with ramen. They had the power supply was like the size of a washing machine. And now with diode lasers like this, you can get by with batteries. So it's not, this isn't as powerful as that one, but it's still pretty powerful. And so this first emission, this happens first spontaneously, and the photon comes out, and then that triggers or stimulates, and that's the key, stimulated emission. That stimulates the next photon to come out, and then the next one. The stimulated emission is amplifying that first photon. They're in phase with each other because they're in that resonant cavity. And then the third one, and then the fourth one. So you see that's building up a light amplitude. Now the amplitude, this is where we get sloppy in our language. We're talking about individual photons, so that's treating light like a particle, okay, when we talk about photons. But what does it mean for a photon to be in phase? In phase is a wave description of light. So we do say that. We say these photons are in phase with each other, but what we really mean is we're building up a light wave that has a huge amplitude. The amplitude is proportional to the number of photons. So if you have a really high amplitude light wave, that's just another way of saying you have a lot of photons that are in phase with each other. And this in-phase nature really allows that amplification to take place, because if they were out of phase with each other, they would interfere with each other and kind of destroy each other. Now, the energy can't be created or destroyed, so another way to describe this is they destroy the linearity of that laser. They might interfere with each other to where they're not going in the same direction, and so they appear at different angles. And so there's not any energy lost, but energy along the direction of the beam is lost. And so if they're out of phase, then they diverge and they go off in different angles. Then they're not in the resonant cavity anymore. Then you lose the power of the laser. So that's also how interference works too. When it's happening, when light interferes at the beam splitter and there's no light coming out, those photons didn't go away. They went off on different angles. You kind of think of it as a collisional model. When they're out of phase, they collide and then they go off on different angles, and it reduces the power along the beam line. So this is our danger classification. Since the student made this, I don't know what the actual classification of this is. I just know from experience with lasers that this one is sort of bleaching out my vision more than the eye-safe lasers, and so I assume this one's not eye-safe. I haven't measured its power, but it's better to be safe than sorry. So class 1 lasers are safe for all use. Class 1M, again, is safe, but don't use a magnifier, like don't shoot it into a lens and then into your eye. A class 2 laser, 1 milliwatt, is a laser pointer. Don't stare into the beam, but it can hit you in the eye and cause mild irritation. So it's one that'll make you flinch. Notice if this was that bright, you couldn't look at it without flinching, like you would look away from it. Now I can look at that one without flinching, And so I'm not quite at the point of a class 3R where I have to squint and turn my head. Okay. It was kind of funny when I worked at Pentex. They had rules for everything. They had so many rules, you were probably breaking a rule any time of day or night. And so I was trying to get approval for bringing these 2 laser Raman spectrometers, these portable Raman spectrometers, on to buy them. I needed their approval to buy them. And this person came to go through the paperwork with me, and they were in my office, and they were asking about the safety of these lasers. And I said, well, you know, I think those were probably, you know, class 3B. They were built in a probe that had a built-in magnifier. So yeah, you could put it on your skin and it would burn, like it would be hot. You would move it before you actually damage the skin. But it was a pretty powerful laser. And I didn't know I had to fill this paperwork out. So this person put a stop on my purchase and came to my office and fussed at me for not reading the laser policy or whatever, and said, every laser that's purchased here needs to go through our office, you know, right? And I said, really? And they said, yes. And I said, even laser pointers? And they said, yes. And I said, really? Even though they're not damaging to the eye? I pulled one out of my drawer, and she was like, oh, you have a laser pointer. I said, yeah, and it's mildly irritating, and I shined it in my face. And I was like, it was just like electrically shocked the person. She was like, you know, it's like, it's a laser pointer. Don't stare into the beam, but it's mildly irritating. So, but yeah, when you get up to class 3B and class 4 lasers, they pack a wallop. And why is that? It's because it's directed energy. All of that emission is sent in a straight line. And so that's the point. When we talk about military applications, the generic category of lasers is called directed energy weapons. And so when you're directing all of that energy in a particular direction, that's what we're talking about. And most of the time, that's using a laser type system. They have other kinds of lasers that are not visible. They have microwave lasers or masers, okay? And they most of them are visible for various reasons, but then there's a lot of infrared lasers that you can't see the beam, and they can do quite a bit of damage. We had a pulse laser system that was in the infrared when I was in graduate school, and it went from one laser table to another. And we typically had a PVC pipe that ran between the 2 tables so that you wouldn't walk in front of the beam because it's infrared. You don't see the laser beam there. And one time we were messing around in the lab, I guess, and aligning things, and we had taken that pipe down. And then we started up the laser system again, and it's pulsing its laser. And a friend of ours walked into the lab and walked between those 2 tables. Okay, and he went, pow, pow, pow. It got him 3 times as he walked by. He starts screaming and holding his waist. And we're like, whoa. And so, come here. And so he pulled his shirt up, and it looked like he had cigarette burns. That's how powerful it was. Yeah, so that was definitely damaging to the skin. That was in the infrared. Yeah. And so the paperwork at a business would have been unbelievable for that, yeah. So we didn't have any paperwork in graduate school. We should have probably. It's a long time ago. Statute of limitations, I'm sure. But yeah, so these definitely can damage skin, especially in the infrared. Now, this is one of the first lasers. This is the ruby laser. Okay, so you might have heard of a ruby laser. It's interesting, we call them rubies, but it's actually a sapphire crystal structure. So they have the sapphire crystal structure, and if you dope in their chromium atoms, then that's what gives it the red color, and that's what a ruby is. And so these different gemstones can be darker or lighter depending upon the concentration of the element that gives them their color. So you can have pale rubies or deep red, blood rubies, with lots of chromium in there. These are artificial. These are grown very carefully out of a cauldron, or a little crucible in those crystal growing apparatuses. And so this is the flash lamp. This time the flash lamp is a little curly, looks like a curly ball, but it's a piece of blown glass that goes around the ruby crystal. And so that's our first laser. It's 1964, I think. So we pump that cavity, get it to a population inversion. Now, one way we've made lasers more powerful is this idea of Q switching. Because spontaneous emission is hard to avoid. Remember, spontaneous emission is just that element emitting its photon. And so we'll put an absorptive element here, this thing called a Q switch, And we will absorb those spontaneous photons until it's the right time that we want everything to crash down. And so this spontaneous photon comes along and gets absorbed, and that keeps the laser rod from de-exciting. And so we build up that population inversion, 100 times stronger than we could get without the Q switch. And that's how we have these pulsed lasers. That's how we get that much energy out of that infrared laser. And then we turn that Q switch to where it's transparent, and the next photon comes through and hits that resonator and comes back through the medium. We had pulsed lasers in my lab. The reason it hit that person 3 times as they walked by was because it was firing at 10 hertz, so 10 times per second. And so our lab was very annoying to work in. It was like, and if you were to time what I just did, I bet it's exactly at 10 hertz, because that's what we heard all the time for weeks on end, because it's just firing out, those pulses, 10 pulses per second. And then the width of those pulses. So this switch, this on-off switch, would be on and then off, on and then off. And this was 10 hertz. So 1, 2, 3, ... 10 hertz. So 10 pulses per second. And the width of this pulse was 10 nanoseconds. So that was amazing. It put that much energy into 10 nanoseconds. And so it was only millijoules. It was very, very weak, like a weak LED, maybe the kind of LED you would have on a power strip, just a tiny little LED that tells you it's on. So that's, a few millijoules was the energy that it was putting, but it was putting it into 10 nanoseconds. And what is watts? Watts is joules per second. So if you put a few millijoules into 10 nanoseconds, you get up into megawatts of power. So a molecule being hit by this was hit by the wave, the amplitude of something that was like a megawatt of power. And we were doing Raman spectroscopy, and so we were hitting it with billions of photons, and we were getting a lot of signal out. That's a way to get your signal up, is by hitting it with more power. But you don't want to destroy the molecule, so you only give it that much energy for 10 nanoseconds. And so we're shaking that electron cloud. It's kind of like beating that molecule and getting the change out of his pockets. We're like, yeah. And then the photons are coming out, change is flying out. We're getting all the spectroscopy, but we're just banging it with a lot of tiny little energy, but in a really small amount of time. Now then we go, this is revolutionary, these diode lasers. And so the light emitting diodes, if we put those in a resonant cavity, you can create a laser out of any diode. You just have to put it in a resonant cavity. I've got a fun little book that was written in the 70s, well, maybe 80s. It's a Laser Experimenter's Handbook. It's a little paperback where it shows you how to sand down an LED, and polish that surface and make a light-emitting diode out of an LED. It's pretty cool. So I've always wanted to do that. It's another bucket list item of mine. Okay. And so this are all the different parts for light-emitting diodes. Sometimes they make the front and the back of the diode this partially mirrored surface, and in the back too. So and then
Britney Spears died.
Yeah, and so that's where I got this picture. Yeah, so I was looking for a picture of a laser diode, and I thought this was a really good picture, but that happens to be the Britney Spears guy for semiconductors physics. So I used to have that video of the guy like, leave Britney alone, but I don't know if y'all remember that. So I cut that video this year. But yeah, so then you have a partially silvered surface on the front, and then that builds up that population inversion. And you have this tiny little diode laser. And for my research in graduate school, we had an infrared diode laser, and we could scan the frequency by changing the temperature of the light emitting diode. And so we put it on a little cold finger, we cool it down, and we would control the temperature. And as the temperature ramped up, the dimension would change. And so the resonant cavity would change. And we could scan about half a wave number in frequency. so we would scan a half a wave number several times and get my spectra, and then we would change the bulk temperature of the whole thing and move it over to a different half wave number region, and then we would scan that one. We'd move it over a half a wave number, and then we'd scan a half a wave number. So we were piecing together our spectrum a half a wave number at a time. Incredibly tedious. It took us 2 days to get our data, and I had like 1,200 spectral lines and about 4 wave numbers. And anyway, that was pretty interesting that we were tuning the laser by changing its dimension. So this is the littlest laser. This is the diode laser. You can see that it looks like an LED. It's shown with a penny here just to give you the scale of things. So that's a diode laser. And then this is the largest laser in existence. This is the National Ignition Facility. So there's something like 92 beam lines here, 92 lasers all across the middle here. And it's so big, this is a person for scale. So here's a little maintenance person down there doing some work. It's just about 1.5 football fields, so 150 yards long building. And we can watch one of these movies here. So what this is doing is this is trying to study laser fusion. So they're taking all of these lasers and they're compressing lithium deuterium or lithium deuteride pellet with the light. And so light is weird. It doesn't have mass, but it has momentum. Isn't that strange? I mean, momentum, if you want to remember physics class we all love, is momentum is mv. Okay? And so how does light have momentum without having mass? And it's just one of those peculiar properties of light. And so if it has momentum, then conservation of momentum is a thing. And so you can have that light be absorbed by something, and when it's absorbed by something, it has imparted its momentum to that something. And so there's such a thing as light pressure. So if we want to compress this tablet of lithium deuteride, we can hit it with UV light and compress it and get it to fuse. And so they're creating fusion in the lab in using this laser beam line. That's the ignition part of the National Ignition Facility. So they're doing fusion research. If there's time, we'll come back and watch the video. So here's the ruby crystal, the ruby laser, 1960. Here they just put enough intense light on there, and we have their term symbols and so on, and then you have this resonant output, that laser. So they're able to get a population inversion relative to the ground state. So that's got to be an intense pump light, and they're able to get that output laser. And that wavelength is 694.3 nanometers. So our helium-neon lasers are, close to 700, deep red. Okay, that neodymium YAG laser that I showed earlier, that was the 1964 laser. And its laser is right here at 1.06 microns, or 1064 nanometers. Okay, so 1064 nanometers. What we see, though, is the frequency doubled laser. So if we take this laser beam into certain crystals, I'm just going to draw a crystal here, and that if that crystal changes its, the resonance of its electron cloud twice for every wavelength of the incoming laser, and there are certain materials that do that. They're called birefringent materials, and you can tune their refractive indices, and it's angle dependent. But what you can do is then you can double the frequency. So if this is 1064, this is half of that, 532. And so that's a frequency doubling crystal. So you take the 1064 light and you put it into this doubling crystal, and you get 532 nanometer light out, and that's deep green. So a lot of your green lasers are neodymium YAG lasers that are doubled, that are frequency doubled. Green is a energetic enough photon to cause fluorescence in a lot of materials, and so this is really good for forensic lighting. So a lot of forensic laser lights, you go into a room looking for biological evidence, and you turn the lights out, you put on orange glasses, and you shine this green laser around, and you see all the fluorescent light. So bodily fluids will fluoresce. In fact, if you want to remain blissfully ignorant, don't ever do this. But if you ever go into a hotel room with a black light, you will never stay in a hotel room again. Okay. And so that's, you know, and in fact, that's what makes the crime scene difficult sometimes in a hotel room, because there's biological evidence everywhere. Okay. You don't want to know that. And so you could double this again to get to 264. And so then you get into the UV. Then we have the helium-neon laser. This is a really bizarre one. We pump the helium atoms, okay, with the light, and then they collide with the neon atoms and transfer their excitation energy to the neon. We haven't really talked about that, but collisional energy transfer is a thing too. And it's pressure dependent, so they have a little gas tube and they get the pressures just right. So we pump the helium up, and then they collide with a neon atom, and now the neon atom is excited. Okay, and then you have, again, a population inversion with an unpopulated level. So you've got probably most of the neon atoms down here in the ground state, tons of those, okay, but you just get a few neon atoms up here, and then you can create a laser between these two levels here. And so one of those is 1200 nanometers, and another one is 632 nanometers. So the helium-neon laser is 632, the ruby laser is 694, and we don't see the neodymium primary laser. We have to double it to get it into the visible range, to get it to 532. And there have been lasers created out of a whole bunch of different materials. So here's just a nice laser selection guide. In the visible region, you have the helium-neon lasers. There's several lines associated with that. I realize the printing is really small. You probably can't see it. You have argon lasers that get into the blue region. Krypton lasers, the ruby laser here, gold vapor, that's kind of cool. I've never seen that laser before. Copper vapor. Then you have CO2. Where's the CO2? Let's see. Here's the, let's see. YAG. Oh yeah, here, 10 microns. So the CO2 laser, because CO2 is so cheap, and this makes a really powerful laser, a lot of your industrial lasers are CO2 lasers. In fact, nowadays you can buy these things pretty cheaply. I can't remember the cost, but if you just Google cheap laser cutter or whatever, you can get these little laser cutting CO2 lasers. It's like a plotter. You put a piece of thin wood there and it'll cut out shapes and everything. It'll engrave stuff, and that's a CO2 laser going through a fiber optic. Okay. Now down below, notice these are broad ranges, and these are dye lasers or tunable lasers. So that is pretty cool. So in this area we can have tunable lasers below here. Now the way we tune the lasers is we set up the resonant cavity here with the output, and then we put inside that cavity a monochromator. And so we might have red, green, and blue. And we could tune that monochromator inside the resonant cavity to make it resonant with red or green or blue. And so that's how you would tune your laser. You would have a laser medium inside a resonant cavity that's tunable. And that's pretty slick. Sometimes you could have solid tunable lasers like the titanium sapphire laser, or you could have liquid ones where you have a dye, an organic dye, and you spray that into the resonant cavity. We had a dye laser where the lasing medium was a spray of liquid with a dye in it, a Rodeman 6G dye, and we had the pump was pumping that spray and the tunable cavity, and it was emitting, and it was all happening just in a millisecond while that dye is passing through the laser beam. You had the pump laser and then the dye output laser. So Pretty cool. Now notice there's a pretty big gap here in the mid-infrared. That's where our infrared spectra are, and that's where we want to do a lot of our spectroscopy for molecules. There's a carbon monoxide laser, but it's just a pretty narrow range, and this is where money is needed, or where science is needed. If you could come up with better tunable mid-infrared lasers, then you have job security. Now let's talk about some interesting lasers. We know that there's a population inversion that's necessary, and one way to get an easy population inversion is to not have it compete with the ground state, right? So if you're competing with the ground state and you're trying to get an inversion relative to the ground state, I wonder what that noise is, then it's a difficult thing. You have to have a super efficient pump. But if you're not competing with the ground state, that's another way to get a population inversion. That's how the neodymium YAG laser works. Another way is an Exciplex, or an excited state complex. You hear these two names sort of used interchangeably. There's also an Eximer laser, but it uses the same idea. That's an excited dimer. Okay. And so let's look at the energy level diagram here. So this is an argon fluorine Exciplex laser. And this is a pretty crazy thing. The excited state potential energy surface looks like this. You see how that's bound? It has this dip here. But when that fluorine is no longer excited, then you have an unbound state and dissociates. So there is no ground state. The ground state for an argon-fluorine bond is not bound. So there is no ground state argon-fluorine molecule. There only exists in the excited state. So that's why we call it an excited complex, or excited, or Exciplex laser, or excited dimer, an argon-fluorine dimer. These are some of the most powerful lasers because you excite the fluorine, which is easy to do, and you put it in contact with argon gas. They form the molecule, they emit light and dissociate, and ready to go again. And so all you have to do is mix these gases, and as soon as those gases mix inside a resonant cavity, you start emitting photons. And so this is a fast way to create a laser. It's a low energy way to create a laser. You're just mixing gases. You're not trying to pump them with an enormous amount of light. And so that's why these have been used to make directed energy weapons. These are gas Exciplex lasers. We also use these to do laser surgery. And so whenever you go in for LASIK surgery on your eye, they cut the cornea, not all the way through, but they cut it and they flap it open, and they ablate or destroy parts of the cornea, and it just evaporates out. They're hitting it with a UV laser and taking cells out of your cornea, and then they flap it back. Now, why are they doing that? Well, because you want this beautiful lens shape. And if you have astigmatism, your lens is misshapen. You've got like a ridge. Most of the time it's a ridge instead of a nice spherical shape. And so they'll just blast that ridge down. Well, they don't want to destroy the outside of the cornea. So they cut the flap open and they cut out the little bit of the inside of the cornea. And all this is done with computer-aided tomography or topography. So they take a scan of your eye. The computer decides how much it's going to ablate from every location. They open the eye flap, they ablate it away, they close the eye flap, put a protective contact lens over it, and your eye recovers in a couple of days, maybe a week. My wife had this done, and I was in there with the doctor. I was like, oh, okay, tell me everything that's going on. And so he had her like strapped down in a little thing, and they make you, they hold your eyes open, and they say, don't blink, don't blink, don't blink, don't blink. Okay, it's over. Okay. And then I was in the control room watching the laser shoot into my wife's eye, and he put like a Sharpie mark on the white part of her eye, on the sclera of her eye, and that's what the computer locked onto. Okay, and over on the left, I could see her eye moving around because it was being blasted with a laser. Right, all her muscles were kind of twitching a little bit. She wasn't blinking, but her eye was moving, and yet over here on the computer, the lens on that laser was following her eye. So no matter what her eye did, that lens was keeping up. It was pretty cool. So her eye was perfectly still over here on the eye, on the laser side, because the laser was tracking with her eye movement. And I said, how fast can that laser track compared to her eye moving? And he said, the laser is about 10 times faster than her eye. So the eye moves over here really slowly compared to the laser, and the laser's like, yeah, I got you. I'm following you around, no matter what your eye does. But if she sneezes or blinks or whatever, then that's too dramatic of a motion. And if the laser loses lock, it doesn't shoot. Okay, so it's pretty cool. And then there was a little crosshatch zone. And I was like, what's that? And he said, that's an area where the laser shouldn't shoot. That's the flap, the hinge of that flap. And so they don't want to shoot the flap and have that thing come off. And so he had a little cross-hatched area there. And so it was just going, doo -doo. And I couldn't see, it's a UV laser. You can't see it in the visible region. You couldn't see it on the camera, but you could see some blue flashes. So I could see some fluorescence of the cells that were getting blasted out of her eye. And it was so cool. But that was an Exciplex, an argon laser, excited. It wasn't an argon fluorine laser, but it was a similar kind of laser. So very powerful laser, very fast laser. And these are our anti-ballistic missile lasers. This is the 747. This is our Missile Defense Agency here, MDA. I bet you didn't even know we had that. You could Google that. Missile Defense Agency. Now they've since canceled the program, but that's a 747 with a laser on it. So we had a 747, the interior guts, take out all the passenger seats, put in all the equipment, the power supply, and everything like that. And it's a single laser, and out the front, they had to move the pilots up, and so where the cockpit was, they put this turret that could shoot a laser shoot a missile in its boost phase. So the idea for this weapon would be something like an intercontinental missile on the launch pad is being shot towards a place you don't want it to be shot towards, and then this shoots a laser beam into the side and burns through where the solid fuel is. And so then once it burns a hole in the metal, then the solid fuel catches on fire and destroys the missile in boost phase. It only works when you still have fuel on board. So it doesn't work in the apogee or in the re-entry phase. Yeah.
Is this the same laser that they're experimenting with the artillery shells? They can track the shells coming in and they hit it with the laser.
Same kind of idea. That's right. And here's one on a C-130. To show how accurate this is a little video that we'll show. So this is a plane, a C-130, shooting the tactical laser. Hopefully the link still works. Okay, so that's the hood of a car, like a Jeep or something. Look how stable the beam is. That's on a plane. It's flying, way up there, and it's burning a hole in a 1 foot square on the hood of a vehicle. Think of the stability, again, with like the eye tracking in the surgery laser, or tracking a spot on a particular item like this. The advantage of this is it's traveling at the speed of light through the atmosphere. So bullets are dramatically slower. So this is, again, the ability to put energy wherever we'll want to put it. So I'll just show those just for interest. Okay. And so let's look at this laser. I said I was going to show how un-eye safe it is. So this is someone's test here. I was looking around at this in the lab, and I started to see some smoke. I'm not staring right at it. Can't get it to really focus. I got it to like char paper in the lab. Anybody see any smoke? It's so bright I don't want to look at it. Anything? No, well. It's incredibly bright though. If we were to turn the lights out, and this would show some fluorescence, but you can't really see the fluorescence because the blue light's so bright. So you need to put on some orange goggles that will block the blue light, and then you can see the red shifted light. So it's a lot of energy. Definitely goes. And it's got a little focusing. There we go. Burn a hole in the wall. We did that in grad school too.